Welcome to the second episode of this series on differential geometry. In this journey, we will explore the core concepts, discuss how to approach the subject, which books can guide you, the common difficulties learners face, and the strategies to overcome them. This is an episodic exploration designed to build your understanding step by step. My name is Shaunak and you're watching this video on my channel Physics for Students. Well, in this second episode, we will learn what is the type of geometry that you need to know what is called differential geometry. And in this process, we are going from the usually Euclidean to non-Euclidean geometry. Well, the Euclidean geometry is familiar to the world that we see around us. For example, the flat space, the straight lines that move on the flat space, the angles of a triangle, they sum up to 180 degrees, and what is called the parallel postulate. Given a line and a point not on that line, there is exactly one line which is parallel to the given line through that point. And the distance that we calculate is using the famous Pythagoras' theorem. The equation that you can see right on the left hand side of your screen is basically a generalization of the Pythagoras' theorem. We also are familiar what is called the congruence and similarity rules, which are side, 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 side angle, side, and this is something which I have read in our school days. But we have to remember one thing, that the world is not drawn on a flat canvas. Yes, it definitely bends, curves, twists, and make a lot of tricky things, and the geometry must evolve with that. So in this part, we will understand from Euclidean certainty to the wonders of non-Euclidean spaces, how things move, what are the concepts, and how we can understand those concepts. So as you can see that first we encounter what is called a spherical or what is called a positive geometry, where the geodesics are converging at a point. So here you can see the space is curved like a sphere. The shortest path between 2 points is not a straight line which you have just seen on a flat space, but it is called a great circle or a great arc. Here the distance becomes a little bit longer, which is this one, d equals to r times arc cos sine theta 1 and so on. And we also get another type of a geometry which is called a hyperbolic geometry, and this is something which is called a negative curvature. It is a saddle shape kind of a geometry. Here you can see the distant formula is a little bit more complex. I have only taken the common version which is used in the Poincare disk model, which is the arc cos hyperbola. So again, as you can see from here, the Pythagoras' theorem is replaced by formulas, because that one is a spherical geometry and this one is a hyperbolic geometry. I apologize for writing hyperbolic geometry as a positive curvature, but definitely it is a negative curvature geometry. We further move in times of Einstein's special relativity, where the space-time geometry looks like this. And in Einstein's theory, we don't talk about distance, but rather we say it is a space-time interval. And here we are taking time as one coordinate and 3 spatial coordinates, and the space-time interval looks something like this, one of the formulas. And here you can see that there is a minus or a negative sign. And this negative sign contributes sufficiently for different types of things like time dilation, length contraction. Well, we are learning differential geometry, so I should not be discussing anything related to special relativity. These are already there on my channel Physics for Students in a special section which is called the Lectures of Special Relativity. So this is what is called the familiar case of Pythagoras' theorem. Here you can see if I draw a kind of a triangle, the sum of the triangles are greater than 180 degrees. Here the sum of the angles are less than 180 degrees. So here this is the spherical and this is a hyperbolic geometry. And this is exactly the type of geometry Einstein used in general theory of relativity. Different shapes, different types of positive, negative and other kinds of curvature. So from here what we can understand that what we started learning is that the differential part we have completed. Calculus, concepts of calculus, books, recommendations. Now you're left with another one which is called the geometry. Now you are going to learn about this, what kind of geometry. So differential geometry is a study of mathematics that moves beyond the comfortable rules of Euclidean geometry and embraces spherical, elliptical and various kinds of geometry. So this is basically opening the door to understand curvature, which is the very heart of differential geometry. And let us open the door to new geometries and let us welcome what we are learning in this part of the video, opening the door to new geometries. Now, when we first open the door, as we move inside a new world, we first find a person who is waiting to greet us. And this person's name is Marvin Jay Greenberg. Well, he is known as one of the best American mathematicians. His works are astounding in terms of geometry and mathematical exposition. He spent his entire life making things which are accessible and easy to students, especially in the areas of Euclidean and non-Euclidean geometry. And Marvin Jay Greenberg is the first person, as we open the door into the unknown world, who will be taking or holding our hand and guiding in something which is a book like this. When we talk of geometry learning, we will first step into this book, which is called Euclidean and Non-Euclidean Geometries, both the development and the history. Well, Marvin Jay Greenberg got his doctoral from Princeton University under the renowned mathematician Sir Lang, and this is the book. You can find out the customer reviews. But before going in the book, I would like to tell you that this book has got several versions. So the first version is this one, second is this, third is this, and the one which is available today in Amazon is the black covered book. So don't worry if you get some other version, these are all the same. The total number of pages are quite dense, total around 665 pages, and it is good. That means the author actually takes a lot of time and patience going in the minute details and explaining you. Well, why do I consider this as the first person, the torchbearer into the world of non-Euclidean geometry? The reason is this one. So this is not only a textbook, it will again get you through a historical and a conceptual journey. It will explain you non-Euclidean geometry and its relation to mathematics and physics, and it will bridge the gap between Euclidean geometry and how you step into the new world of differential geometry. So the core themes are Euclidean geometry. It will revisit, because that is good that you make a kind of a brush up before going in the lessons. Then it will start with the parallel postulate program, which will be showing that centuries have taken mathematicians to prove this one. And then the birth of non-Euclidean geometry, followed by Lobachevsky, Bolyai, Gauss, and other areas. It will also help you to understand the models of non-Euclidean geometry, including Poincare-Desk, upper half, and so on, and the Klein model. And it will also link you geometry and philosophy, which will ask you certain questions of truth, logic, and structure of reality. I have read this book. Honestly speaking, it is an amazing book. It will help you to brush up the basic concepts of Euclidean geometry. It is good that in case you have missed some, and then it will go into the birth, the history, the mathematics, and so on. So these are the customer reviews. I have put a few, I would say, customer reviews from the Amazon, and you can read. These are all 5 stars, remarkable, great content, and so on. So it actually proves that the book is indeed great. Before going into the content and discovering and telling you what this Greenberg's book actually contains about, you can just read those which I have highlighted, because this tells you the objective. Prospective high school and college geometry teachers represent with a rigorous treatment of the foundations of Euclidean geometry and an introduction to hyperbolic geometry. So general education and liberal arts students are introduced to the history and philosophical implications of the discovery. So if you're an art student, a general education, you can even read this book so that you can understand the philosophical implications and a lot of, I would say, stories about the discovery of non-Euclidean. What is important is this, which I highlighted. If students do not do a good number of exercises, they will have difficulty following subsequent chapters. Hence, the book actually tells that you should not skip. You should follow all the exercises, otherwise you won't be able to understand about the pattern, the way, and the concept the book has been arranged, or the basic concepts of non-Euclidean geometry. I will give you a brief synopsis of how this book is arranged. You can see it starts with Euclid's geometry. So this is a brush up, you can say. Euclid of Alexandria, the Pythagoreans, etc. Then it will go in Euclid's first 4 postulates. It will show you what are the attempts have been made to prove the parallel postulate. As you can see on the right hand side, there is a good amount of diagrams which will make the understanding more intuitive and visual. The second chapter is basically what is the logic and incidence geometry, the theorems and proofs, the ifs and thens, how a logic is designed and how a statement is arranged. It will further follow in what is called Hilbert's axioms. So you will find what are the flaws in Euclidean geometry, axioms, betweenness, axiom, etc. So it is nice. Again, it will take you step by step. Further, it moves into what is called a neutral geometry. Now, neutral geometry, I will tell you something which considers all the postulates of Euclid, but not considering the parallel postulates. So this is what neutral geometry is all about. So it will include the Sakarian, Lambert quadrilaterals, angles, sum of triangle, etc. Then you move in the discovery of non-Euclidean geometry. As you can see, the figures of Gauss are there, Riemann, Bolyai, and all the discoverers of non-Euclidean geometry. And I can tell you this is a very famous equation, a statement written by Janus Bolyai. His father was Farkas Bolyai. Out of nothing, I have created a strange new universe. And I can tell you, if you go to my lectures on differential geometry, there's a nice story about the what I would tell the tragedy of Janus Bolyai, why he left mathematics out of shock, and his father's unfortunate role in his Farkas Bolyai, and why he was shocked by his discovery. So it was Janus Bolyai who actually discovered non-Euclidean geometry, and in a letter he wrote this to his father, that out of nothing I have created a strange new world. Amazing history, amazing book. You should go ahead and read this. Geometric transformations, motions and similarities, Klein's Langer program. Again, a wonderful exposition in the geometry and historical developments. Further, you will see that results in real hyperbolic geometry, the curvature of hyperbolic plane, the circumscribed cycle on the triangle, and Bolyai's construction in the hyperbolic plane. Very, very important. So Marvin Jay Greenberg's book gives you a historical, mathematical, with certain inspirational and frustrating stories in the first step in understanding non-Euclidean geometry. The second book which I would recommend is not a very popular one. It is by Ellery B. Golos, and this is the picture of the famous author, and this is a book called Foundations of Euclidean and Non-Euclidean Geometry. The author worked as a professor of mathematics for 40 years in Ohio University, and he actually wrote this wonderful book. So let us look how this book is arranged. This book is arranged in three parts. The first part would be basically tools, insights and motivations to elementary geometry. The second part is basically how the author introduces the rigorous mathematical approach in understanding geometry, and the third part would be basically a detour from Euclidean to non-Euclidean geometry. This is not a very popular book, but I can tell you it is an amazing understanding, a step-by-step approach towards non-Euclidean geometry. This page would give you an insight of how the books is arranged, a basic synopsis of what are called the contents. You can go ahead and read and pause read this book. Part 1, the introduction. Second would be the axiomatic developments, and third coming to the non-Euclidean geometry. What is very, very typical and very important and very subtle in terms of understanding Golos' book is this one which I am highlighting in red. What it tells is that let us define a pencil as a sharp tool used for writing. This satisfies the criterion of simplicity, which means that any definition should use ideas and words that are simple or simpler than the ideas of words being defined. That means he says that to anyone who does not know what a pencil is, the following definition would be incomprehensible if I say a cylindrical instrument tapering to a conical point as employed by an amanuensis. A definition using words more complicated than one defined is not of much use. So that is how he tells that in case of you are writing a definition, you should be careful that it is simply not possible to define every word without getting trapped either in an infinite circle, and dictionary definitions are basically circular in nature. This is something when I read, I underlined, I found it extremely useful. So when you're defining something, out of this statement or writing your proofs in non-Euclidean or differential geometry, be careful. Don't use words like cylindrical instrument, tapering to a conical point. It actually carries no use. And I have further highlighted few of the points and I have summarized here. So what Golas tells in this book is that a good definition of mathematics must satisfy three conditions. One, simplicity. It should be clearly expressed clearly or concisely. There should not be any circularity. That means it should not go and go and go and go. It must not rely on the concept it is trying to define, and uniqueness. It must distinguish the object being defined from all other objects. That means it should be something very unique. So this is a very good learning from Golas' book, and he further writes that he was the greatest mathematician who ever lived. One is not really making a statement that is to such a collection of words the labels true and false do not apply. If the sentence is changed to something, Beethoven was the greatest mathematician who ever lived, or Gauss was the greatest mathematician who ever lived, then the sentence becomes a statement, a collection of words to which the labels true or false may be applied. So this is amazing. Before starting the book, it tells how to write a definition, how the sentences can be changed, and so on. So from this book, what I can tell you, if you read this, that what is the definition of true and false, it is clearly mentioned over there. So here you can see I have just made a basic understanding that a statement is something that can be judged or true or false. So if you're saying that he was the greatest mathematician who ever lived, is too vague. But if you say Gauss was the greatest mathematician who ever lived, then it becomes a statement. Similarly, x is a whole number is not a closed statement until you specify what is the value of x. So this would be Ellery B. Golas' takeaway from the book. Very clear, very well defined, and there is no confusion in understanding the book. The next book which I would suggest, because we are learning the geometry part, is what is called Geometry Illuminated, and this is written by Matthew Harvey, and this is, as you can see, MAA Press. So this is Mathematical Association of America. And why this book is important is that this is one of the best books to build the foundation. It is easy to understand, very clear and simple. The entire chronology of how geometrical thought is developed is very well defined. It is designed as an undergraduate book, so you can start with the basic Euclidean geometry, then go into things. And it is also very good for those students who are comfortable with proofs and rigorous thinking, and it emphasizes visual approach. So a lot of visuals are being defined, and a lot of illustrations makes the thing very, very clear. How the book is arranged? Simple. Part 1 talks about again the neutral geometry, that means not considering the parallel postulate. Part 2 starts with Euclidean geometry. Part 3 goes into transformation from Euclidean to non-Euclidean, and part 4 would be the hyperbolic geometry. So this is a book particularly designed for hyperbolic geometry, and I think that it has done proper judgment in what it claimed to be so. So the part 1, as you can see, you can pause the video and read what it covers in the neutral geometry, axioms, neutral geometry, angles, triangles. So basically it starts with this. Second, it goes with part 2, the Euclidean geometry part. You can again take a pause. I've just given a snapshot of this. What is the part 2 of the Euclidean geometry? Good part is that from Euclidean geometry, part 3 moves into the transformation. So you don't find any problem in analytical geometry, orientation, glide reflections, change of coordinates. Everything is very well defined. So part 3 is the Euclidean transformation, and part 4 is the hyperbolic geometry. With that, the book ends. So hyperbolic geometry is the key, but before that, the book, Matthew Harvey makes an amazing effort, designed, well structured with points, logic, in order to make you understand, and a slow but a gradual transition from Euclidean to non-Euclidean, specifically hyperbolic geometry. So these are the two books which will first open the door to the world of non-Euclidean geometry. Either you can start with Golas' book and then go to Harvey's book, or either way. But these two books are the foundations which will build up in the building up the next steps of understanding differential geometry. So thank you very much for watching. You have taken a time, so please do subscribe to my channel Physics for Students and click on the bell icon so that you get all the notification from Physics for Students. You can follow me on my Facebook handles and you can write to my this email ID. This is episodic videos, so few more to come so that your learning and the foundations of understanding differential geometry is rock solid. See you in the next video, but till then, may the good Lord be with you.